I am by trade an astronomer. I have a PhD in astronomy, and it turns out that if you tell the drunk, overly talkative person on the flight next to you that you're an astrophysicist, this does not deter them. But it does deter most people, but I'm here to say I'm actually just a lamp stack programmer, so be gentle. That was fascinating. So I'm here because I saw Corey Haines tweeting about the conference. I looked at the website. It looked truly awesome. And I put out on Twitter, hey, if you want an astronomer to sit in the back of the room learning a bunch of stuff and then talk science, I'd love to do that. And Tom took me up on it. And so I'm here at the end of the day to switch gears and take you over into the world of where all of this programming has actually allowed us to get. Now, I've been doing astronomy since I was younger than it seems rational to be doing astronomy, which means that I remember when we thought having 4 data points was a lot for many different scientific problems. But as the years have gone by, we've started to get big data sets, like 20 data points sometimes. And it turns out that as we went from a field where 4 data points was a lot to now, I mean, to be entirely honest, we have things like the Sloan Digital Sky Survey, which is millions of data points. It's completely changed how we do astronomy. And I started university with a dad who's a computer scientist, and he's like, you're never going to get a job if you're an astronomer. Get a computer science degree. And so I ended up dual degree computer science and astrophysics, as you do. And it turns out that computer science has been far more useful than anything else in making me a good scientist. And where I started was not here. This is where the field started. So that whole 4 data points, we had people taking glass plate images of the sky, using rulers to measure the width of stars on the glass plates, because the wider the star appeared, the more light interacted with the chemicals. And this is a slow and tedious process. It's both slow to develop glass plates that are exposed to the sky, and then it's slow to sit on the floor and measure everything with a ruler. And so it used to be that in astronomy, when you had a big collaboration, that was you and a buddy and 1 or 2 students. And you'd go to the observatory, you'd get your data, and within a year or 2, you had eked out every bit of science that could possibly come out of your data that you knew of at that point. But this doesn't work anymore. And it actually wasn't the space race that started the change. A lot of people think that's the case. This is Mariner 2. About 52 years ago, this little spacecraft went and visited the planet Venus. And when it did this, it was the first spacecraft, the first anything, to allow us to directly make measurements of another world. And up until this point in time, science fiction writers thought that Venus might be a tropical paradise. It's a little bit closer to the sun. It has that beautiful cloud cover. It shouldn't be that hot. There's probably life. And Mariner 2 broke everybody's hearts. Because it turns out Venus is 900 degrees Fahrenheit. And nothing lives there. And it's also like raining hydrochloric acid and all. It's bad. It's just bad. But Mariner 2 had a whole 600 bytes of magnetic tape that it could store information on. Now, I know I, for one, have tweeted more data than this spacecraft could hold just today. So even with the early space race, we lived in a small data world, and the poor scientists that would dedicate 10 years of their life to seeing this spacecraft launched and getting there would have all the data reduced in like a month. All that waiting for a month. But then things changed. We have this little spacecraft called the Sloan Dynamic Orbiter. It's currently out sitting in this weird gravitational point between the Earth and the Sun where it's balanced so that it stays directly in line between us and that big nearby star threatening to do really bad things to our satellite system. And it sits there looking for things like this. This is called a coronal mass ejection. And if they do this explodey thing while pointed straight at us, this can destroy satellites. It's bad. But because we have SDO out there monitoring the space weather, we know when we need to put our satellites into safety mode. We also know when Quebec needs to turn down the amount of power on its power grid. Some of you may remember in the 80s where suddenly Quebec had no power. That was caused by a solar flare. Turns out if you jiggle the Earth's magnetic field, which the sun can do, that generates more electricity in the power grid, and if your power grid is running at maximum, you black out Quebec or anywhere else that happens to experience this. So sun, nearby star, kind of dangerous. We want to make sure this star doesn't do bad things, and SDO does this to the tune of 600 gigabytes a day. So my laptop holds a terabyte, and about 600 gigabytes of that is random stuff. Now, I have this vision of the scientists at SDO each day being handed a new little tiny weakling MacBook Air and told, you have to be done with this by tomorrow because we're getting more data. Now, this means that we have to write software to solve all of our problems. It means that we're facing a flood of data that is raining down on us from the skies, because that's where we put spaceships, but it's also coming at us through Ethernet cords from all of the ground-based instrumentation out there. And we're trying very hard to figure out how to deal with all of this. And it's a new generation of astronomers, it's my generation in a lot of cases, that's figuring out how to solve this. For astronomy, I'm a baby at 42. I work in a field where the retirement age is actually over 70 on average. We still regularly have people attending meetings in their 80s. They remember from before we knew what galaxies were. They're not the ones solving computational problems. We still like them. But I've been using a computer since I was 3, because my dad builds them. And one of the things that I studied in university was globular clusters. And this is the top quadrant of a globular cluster. They're circular things. And you can see some of the stars in this are changing in brightness. And this was what I studied as an undergrad, these stars that vary over time. And it turns out that as their brightness is changing, they are actually expanding and contracting by large factors. If our sun did this, Mercury would get eaten, well, once, but then the sun would keep going out to where Mercury is. When Keats said he wanted a love as constant as a star, I want you to think of this. Because stars vary greatly, and sometimes they explode. But mathematically, this is the first research paper I ever was part of writing. During one of those, I just finished college, I'm going to get married, oh shit, that didn't stick moments of my life. So my first research paper does not have the last name I've had ever since or before. But anyways, this paper came out of sitting down and going through almost 100 years of journal articles, looking for stars that we'd been studying for 60 or more years, so stars that we'd been studying since before computers were a thing, looking through journals that were often typewritten, and then, because I was an undergrad, typing in all of the numbers from those journal articles, and then looking to see how those stars' pulsation rates had changed over those 60 or more years. Stars like our sun, they shine because of nuclear reactions going on in their core. As these nuclear reactions go on, the overall density of the star changes. That core, it's burning fuel, it's getting denser, the temperatures are varying. And another way to look at this that's actually much simpler is imagine you have a soda bottle, and as you're blowing into it, that sound, that's a resonating cavity. And these stars, they act like a resonating cavity. And instead of hearing a pitch, we're seeing a pulsation rate. Well, if you add or subtract liquid from that soda bottle, it changes the pitch. Well, if you change the density of these stars, it changes the pitch. And so what I did, looking at these stars, mostly because I was an undergrad willing to type in all of those tables, was I didn't know what I was looking at because I was an undergrad. So I made Excel plots of every possible variable I could. I looked at how the periods were changing over time. And what I found was, for no reason that we have still even figured out, when you put all the numbers together, stars that pulsate as like one wave in their outer envelope, if you remember the exercises in physics, any of you who are computer science majors had someone like me force you to take calculus-based physics. If you move a rope just right, you get a single standing wave. Well, that's what half of these stars do. And the other half, it's like you have that double part of the wave, which is much harder to do, and your wrists get sore when you're in physics lab class. For reasons we can't explain, when the star switches between one mode and the other, how it evolves changes. We don't know why, and we wouldn't know about this if it wasn't for digging through the data and just seeing what science is hidden there. And it turns out that a lot of today's biggest discoveries are coming from people saying, I've got a lot of computational power. Let's see what is hiding in the data. And it turns out that's where great science is also hiding. And sometimes great solutions to problems. This is a pretty galaxy. It's a pretty galaxy that is facing us, that has a spiral structure. If you could rotate it sideways, it would look like a plate and be very boring. But facing us straight on, we're able to look down into the center. And hiding in the center of this galaxy is a giant black hole. And this giant black hole in our galaxy is just sort of sitting there going, I'm starving. Can anyone pass me a star? In this galaxy, that black hole is going, I'm eating all the gas. And as it eats all the gas, it is giving off radio emission, it is giving off jets, it is giving off all sorts of high-energy, interesting light. And for a long time, we looked at galaxies like this, and when you look at them with detectors that spread their light out into a rainbow, we'd see sharp, fine lines in different places. This indicates there's hot gas that isn't moving a lot that is giving off emission lines. Basically, there's a whole bunch of open and closed signs orbiting this star, but they're not doing it very fast. So they have narrow lines. But then we'd also see these super broad emission lines, which implies that you have stuff that's zipping around really fast. But that's only for some of them. We called those Seyfert 1s because it was a dude named Seyfert who found them. And we shouldn't be allowed to name things. Then we also found that there's other ones. And these other ones didn't have those narrow lines. Sorry, they didn't have the broad lines. And we were really confused. Why does one have these really thick, blurred out lines, and the others don't? And then sometimes we'd see weird things where the radio jets would have a lobe pointed towards us and one pointed away, and the two ends would appear to be going faster than the speed of light. That's just not allowed. And we call those Bielac objects. And the ones without the broad lines, we call those Seyfert 2 galaxies, because again, we're not allowed to name things. And then there's quasars, which is where you just have a really bright center. And so all of a sudden, we have all of these different things that are sort of similar, but not really, and we're deeply confused, because we only have like 4 or 5 of one and 4 or 5 of the other. But then we started building surveys that would look at a quarter of the sky or more. And we'd start to catch face on, slightly more edge on, slightly more edge on, completely edge on. And what we realized is all of these objects are the exact same thing. And what was different was how we looked at them. When we looked straight down the throat of that feeding black hole, we were seeing some of the gas that it spit out, and those are the narrow lines. Now, if it's spitting it out, you rotate it sideways, you still see that stuff. But when you rotate it sideways, you don't see down into the core. And the gas in the core that's violently orbiting that black hole as it's about to be consumed, it's moving super fast. And that's where the broad lines were coming from, because some of it was whipping more away, some of it was whipping more nearby, and all of these different velocities that spread the lines out due to this thing called the Doppler shift. This is why fire trucks make the noise. Physics. But what's awesome is, as we got more and more data, we were able to find these transition objects. We started naming them Seyfert 1.2, Seyfert 1.8. We had a problem, but the problem led to a solution of they're all the same thing. Now, we also had this problem known as where are things in space? We can't take a tape measure and measure the distance to Mercury. But with Mercury, at least, we can fire radar off of it and just measure how long it takes for the radar return, and we know where Mercury is. We're good. Pluto is a bit problematic. We figured it out a month or two before New Horizons got there. I am not kidding. Stars and other stuff? Well, we actually rely on those pulsating variable stars. That's why I got into this field. I was inspired as an 8th grader who read too much stuff about the woman who first figured out, Henrietta Leavitt, that a star that's pulsating, if it's pulsating very slowly, turns out it's actually a whole lot bigger, a whole lot brighter. If it's doing it quickly, it's smaller, it's fainter. And these are kind of like standard candles. So imagine if every 100-watt light bulb beat 10 times a minute. First of all, it would be annoying. Second of all, kind of useful, but annoying. Now imagine if every 60-watt bulb was 6 times a minute. Well, that's the opposite in brightness to the way pulsating variable stars work, but it's still useful information. And this is the idea behind how we measure the distance to the nearby galaxies. We look for these pulsating variable stars. This is how Hubble did it. Hubble figured out our universe is expanding by measuring pulsating variable stars in nearby galaxies and realizing nearby galaxies weren't moving as fast. More distant galaxies were moving faster away from us. And it's sort of like if each chair in this room, during each talk, got 1 inch between the chairs. By the end of the day, we had 6 or 7 talks. So each of the chairs would be 6 or 7 inches apart. You two, if you'd sat there the whole day, which you didn't, but that's okay, you would have been 6 inches apart at the end of the day. You two, you have 1, 2, 3 spaces, so you would have been 18 inches apart by the end of the day. The bigger the distance, the greater the velocity that things appear to move. Kind of cool, but stops working when you can no longer see the variable stars. But then we got lucky. This dude named Chandrasekhar, super genius guy, on the boat from India to England to go to graduate school. He got bored and did math. And while bored and doing math, he realized that if you make a high-density star, what's called a white dwarf, sufficiently big, the protons and electrons in this star are no longer capable of shoving each other apart. And when this happens, they violently decide to become a neutron, give off a bunch of energy, and what was a white dwarf, when it hits 1.44 times the mass of the sun, becomes a neutron star in a giant fiery explosion. That is why you shouldn't listen to Keats about love. Now, this is a way of creating what's called a type 1a supernova, which is what's seen in this picture. And we can, with the biggest telescopes in the world, and off of the world, we use those too, see these exploding stars so far away that we're looking back a significant fraction of how long the universe has been around. Because it takes time for the light to get us So the most distant things, we're actually looking back in time. And so this means that when we're studying that, we're studying how the universe's behavior has changed over time. And when we first started looking at this, one of the big questions we had, one of the questions we didn't know the answer to when I was an undergrad, is does our universe end in fire or ice? Is it going to expand forever? Is it going to expand and stop? Is it going to expand and crunch back in on itself? We just didn't know. And we started learning, it looks like it's probably going to expand and stop. That's what the maths were looking like. And the reason I say this is because when we did the maths, we assumed that everything in the universe was regular matter, dark matter, and there was no other random forces tearing us apart. We were wrong, but the math was easier this way. And then in 1998, this plot was published by a then graduate student, was lead author by the name of Adam Riess. This is one of the two key papers. There were two competing teams at the time working to study the expansion rate of the universe as a function of time to try and figure out, are we slowing down over time or are we going roughly the same speed? Those were the only two things we thought were options. And when Adam made this plot, that omega lambda means something very different in astronomy. To us, lambda is the constant on the shape of the universe's calculus integral. You throw that constant on when you do the integral because calculus, blame Newton. And Einstein put it in there as well, maybe this is how we stop the universe from expanding, because he was into steady state. And then we realized Hubble, universe expanding, we threw out lambda, we set it to 0. And then while Adam was making this plot, he realized, well, crap, that integral actually has a constant tacked onto the end of it that physics doesn't account for. And because astronomers shouldn't be allowed to name things, we named that stuff that's responsible for what turns out to be the accelerating expansion of our universe. We named it dark energy, which means nothing. It is not dark. We don't know if it's energy. What we do know, because we finally had enough supernova out to a great enough distance, is our universe is expanding itself apart at an accelerating rate. And that's kind of awesome. But not all of the discoveries that we've made have been so far out. Some of them are actually pretty close to home. Now, humans have known for as long as we've had the capacity to look up, which probably predates humans, we've got a few planets. We have Mercury, you can see it. Venus, you can see it. Earth, we're hopefully standing on it. Mars, out there being big and red. Jupiter, Saturn. We can see all of those with our eyes. This is all of them. What we didn't know is if there were other star systems out there. And now we can take pictures like this. This is an actual image taken by a radio telescope in the Atacama Desert called ALMA in the millimeter wavelengths of light. So there's no biological that we know of can see in this color. The orangey bits, that's all gas. The black circles are where young planets in the process of still forming have cleared their orbits. That means they're planets, even according to the IAU, which demoted Pluto because it didn't have the decency to clear its orbit. These are planets. And what's amazing, I remember my senior year of high school, because I was a nerd, I was working at a local observatory, reducing radio data as a senior in high school, as you do. And as I'm sitting at my old school Spark station, my advisor comes tearing in, and he's like, we found planets around pulsars. This was back in 91, 92. And these are basically lumps of burnt out chunks. You know how Vulcan died? Yeah, think that. That's what we were looking at. But it was the first time we found something orbiting a star that wasn't another star. This is not all, but many of the solar systems that have been discovered by the Kepler spacecraft, shown against our own solar system for scale. We used to believe, way back in the good old days, known as the 90s, that solar systems were like ours, rocky planets in near the stars, but not too close, gas giants further out. And we were totally wrong. And anyone who tries to tell you we understand how solar systems were formed is either about to get a Nobel Prize or is wrong. Because the more Kepler has studied our universe, the more we realize we as human beings lack the creativity to see what our universe is capable of creating with a bit of gas, dust, and physics. These are all different, with different numbers of central stars, different numbers of planets, in all different size ratios. It's nothing like anything we imagined. And we're finding planets around tiny stars, giant stars, all the stars, binary stars. Tatooine could be out there. But it even gets cool even closer. There's a great guy by the name of Michael Brown. He's one of many famous Michael Browns, not the one who died in Ferguson, but rather the one who's a Caltech astrophysicist is the one I'm talking about. You should know about both. One killed Pluto, the other one I'm not going to go into. Pluto killer, Mike Brown, along with killing Pluto, discovered this little object called Haumea. It's what is shown in the rather horrible picture on the right, along with one of its many moons. This is an object that is shown to scale with all the other big Kuiper Belt objects out there. Pluto's not the biggest of the Kuiper Belt objects anymore. It kind of had it coming when it lost its planethood. Haumea is a weird one, though. We can watch it pass in front of background stars. And when it does this, we can measure how long it takes for the star to come back to being seen. And sometimes it's one amount of time, and sometimes it's another amount of time, because this sucker's an oval. This is not normal. And it's like spinning really fast. And there's reasons. And the reasons took computer models to figure out. So here are our normal planets: Mercury, Venus, Earth, Mars, down in the center, Jupiter, Saturn, Uranus, Neptune, starting to bring in Pluto. That's not Pluto, sorry, that's Haumea. And then we started finding all of this other stuff out there with similar orbits. But the orbits didn't align, but they all had kind of similar, how elliptical they were, kind of similar tilts relative to the sun. And there was a ton of stuff of all these different sizes, more tiny stuff than big stuff. And it was all super shiny. And shiny both means, oh my gosh, that's awesome in the firefly sense, but it also means it hasn't been exposed to the sun long enough for organic molecules to form on the surface and make it look like dirty snow. So something caused all of these objects to be like new snow on their surface. And it turns out that if you take this system, and hopefully it will do this in a moment, this video is always slower than I remember it being. If you take all of those orbits and you precess them in time, because these ellipses are all rotating, if you precess them back in time, it turns out that at a point many 100,000 years ago, something beat the shit out of Haumea, broke it into a bazillion little pieces, or at least several hundred, made it shiny, and over time, all of that scattered remnants has scattered around our outer solar system. we're able to figure this out because we now have the computer power to go, okay, we have all these shiny objects. Could they be related? Let's model it. And it was just that simple. Query database of Kuiper Belt objects. Find all that are shiny. Precess. And that's how we discovered the collision that sent Haumea spinning. Now, what's really cool is this same idea of let's look at the orbits and see what they can tell us, led to Michael Brown realizing that where he can take away a planet, he can also give a planet. So earlier this year, in January actually, I was at a NASA meeting when this occurred, and they interrupted the entire meeting and told us to get on Twitter. And then I had to give a talk. So I'm giving a talk while everyone's on Twitter. And I wanted to be on Twitter with them was the real problem. So what Mike Brown had done is he's been finding all of these small blobs of ice of very varying shiny amounts out in the outer solar system. And he discovered a whole bunch of them all seem to be pointed in one direction. And if you rotate the solar system in your head and add in a few comets, I don't know why the one graphic has comets and the other one doesn't. Anyways, if you rotate the solar system, you find that they're still oriented really strange. And this shouldn't be stable. If you take a whole bunch of objects and let them go, they will randomize their orbits like I just showed you with Haumea. These are not random. These are all happily pointing in one direction, which means there's got to be something on the other side counterbalancing all of these orbits. So first the data said, there's something else out here, and it's probably twice the size of Neptune, so pay attention. Now the next thing he did, lots of words for those who like words. I think these are the only words in my talk. He went through and he plotted what are all the possible orbits, all of the places in the sky Planet 9 could possibly appear. And then he went through all of our existing surveys of data. And he used software to search for Planet 9 and to also search for all of the things he'd already found to make sure they could be recovered. He didn't find anything new, which I think made him sad. And he didn't find Planet 9. And he recovered all of his known discoveries using software that didn't know about his known discoveries. So he knows the software works. And using existing surveys, he ruled out everywhere except for where the black is. So now we know exactly on the sky where, unfortunately, in a fairly large chunk of the sky, there's a 9th planet out in our solar system, being twice the size of Jupiter, hanging out, really cold, waiting for someone to find it and name it. Kind of cool, isn't it? Now, all of these different problems, these are problems where we've had a scientist who said, I have access to data. No one has done this database query before. I am going to make this query and do science. But there's so much out there, and you have to have looked at the data and analyzed it enough to get everything into the database before you can do the science. Now the problem is we have things like the moon, a nice rocky surface, and software looks at that rocky surface and goes, yeah, I can't do this. Our best software right now is about 75% accurate on identifying things like craters on the entire surface. Software gets confused by texture changes, sun angle changes, crater on a hill, crater on a flat, soil color changes. And the software can't deal with this, but our human brains can. Turns out there's a ton of problems like this, where the science hasn't been done simply because we don't have enough scientists. I realized while working in Boston, there were as many programmers working at Adobe in their Newton office as there were astrophysicists in the United States. There's not a lot of us. So we have this big problem coming as scientists, and it's called the Large Synoptic Survey Telescope, currently being built in Chile, because that's where we build things. It's going to be 8 meters. It's not the biggest. We have bigger, and we're building bigger. But what it's going to have is a 3 billion pixel camera that is going to study the entire sky every 4 nights. And I keep trying to drop the 0 off this number of terabytes because my brain just can't grasp this. It's going to collect 30 terabytes per night. Cisco is having to develop brand new technologies to figure out how to deal with this. And we're going to have to do as much data reduction as we can in real time, because how do you store 30 terabytes collected per day? You just don't. So one of the ways that we're working to deal with this is to create, and this is where my job comes in today, we're trying to create places where we go, all of you, you're occasionally places where you're bored and have internet. Instead of playing whatever is the in thing to play right now, I don't know. I apparently don't play enough video games. Anyways, whatever is the new cool thing to do, or instead of going and doing BuzzFeed quizzes or whatever it is you do, go to CosmoQuest and help us reduce these images. We currently have projects up to look at the Moon, Mercury, Vesta, Mars, and we're asking your help to map out other worlds. And we're working with science teams that are using these maps to solve a variety of different scientific problems. And this is at first order what it is. You do a tutorial, you do an activity, we have comparison images, we give you feedback, and then we publish the research. But that's like how you work with your professional scientist peers. We recognize that we want to build a relationship with people, so we treat them like we treat our beloved students, not the crap students that we wish wouldn't grade grub. So we work by creating curated classroom materials so that kids that are learning this stuff in school can be told, and hey, as homework, why don't you go home and help NASA? Imagine that in 6th grade, going home to help NASA. That suddenly makes homework a lot more interesting. But we teach them the concepts with the help of their teacher. We have online classes for adults. We are even working with planetariums to start creating theatrical trailers so that people in museums can learn about these possibilities. And with CosmoQuest, we're working to create a virtual research center where our students are you, and where we engage you in all the ways that we engage our students. And one of the reasons that I'm excited to talk about this is we have a project that's going to hopefully get started towards the end of the year, where there is old code. And when I say old code, I'm talking about code that has been passed down in Fortran 66 from generation of grad student to grad student. And this code, you tell it what chemicals, what atoms went into the formation of a planet, and how much mass the planet has, and how close to a sun it is, and it comes back and goes habitable, not habitable, which is awesome. But it turns out when you give this code to scientists, because it takes so long to run, they only test worlds that have like compositions that we think know exist, except didn't I tell you earlier that if someone tells you they know how planets form, they're lying? So it turns out there's actual planets that we don't know if they're capable of holding life or not. So what we're going to do is, working with Llewellyn-Falco, have a mob programming retreat where people come to learn mob programming. But the code we're going to be working on is we're going to look at the functionality of that Fortran code and not use it. And write fresh code that then will go and run on individual people's computers, where they can like type in the characteristics of Tatooine and find out if it would have actually supported life. So we're not just doing come to our site and click on pictures of the moon. We're also going to be looking to leverage the intellectual capital of people who just want to learn and solve an interesting problem and help us figure out where out there might there be life? So I hope that in the future I'll get to work with some of you. And wouldn't it be cool to say, hey, I'm going to learn mob programming while working for NASA? So I hope to see many of you in the future. But until then, know that databases, this is where the astronomers truly live. Thank you.